Hi, this is your Vector FIP Quiz Solutions, which you are probably watching on November 10th, 2015 or later. Our first question is this. Planning to scale the building one fine autumn morning, you're searching for a ladder. If the top of the building is 3.5 meters high and you plan to block the ladder out 1.75 meters from the bottom of the wall, how long a ladder will you need? What will be the angle that the ladder makes with the ground? This is a pretty straightforward perpendicular vector solution. So we have a distance of 1.75 meters on the x-axis and a distance of 3.5 meters on the y-axis. We are, of course, looking for the resultant, which is going to be right there. We're also looking for the angle, theta, that the ladder makes with the ground. Okay, so the first thing to remember is that our resultant, as usual, is equal to the square root of delta x squared plus delta y squared. In this case, that means r is equal to the square root of 1.75 meters squared plus 3.5 meters squared, giving us a value for r of 3.913118961 meters. We'll take the sig figs at the end. What about the angle that the ladder makes with the ground? We're going to use an inverse tangent function. Because we're looking at this angle, we're going to use our 3.5 as our opposite and 1.75 as our adjacent. So the inverse tangent of 3.5 meters over 1.75 meters gives us a theta of 63.43494882 degrees. Now, to get our final answer, we need to consider both sig figs and how we will describe our heading. So with sig figs, we would say that we need a 3.9 meter ladder because we are limited to 2 sig figs based on that, and that our angle theta would be 63 degrees. The best way to describe an angle like this is probably with its relationship to the ground or the horizon. So you would say that that was 63 degrees above the horizon or above the surface of the ground. Either one is acceptable. Note, there's no compass rose in this problem, so you can't say that this is north of west. It's just above the ground. We have no idea what direction the ladder is facing. Okay, on to number 2. This one is a problem where you're breaking down vectors or going the opposite direction of what you did in the last problem, where you were finding the resultant. Here you're given the resultant and asked to find one of the components. Your pet parakeet has escaped and is flying at 14 meters per second, 37 degrees above the horizon. How fast must you run in order to stay directly beneath her? So we're given this, which is our, of course, overall velocity for the bird, and the angle. What we need to find is the x component of this velocity, which would be how fast you'll need to go to stay directly underneath her. We'll call it v sub x. Since all we have here is a resultant and an angle, we have to rely on a function that involves the hypotenuse and one of the other sides. Because v sub x is adjacent to our angle, we're going to use cosine. And we know that the cosine of theta is equal to v sub x over the total velocity. That means that we can solve for v sub x by multiplying both sides by v. Cosine of theta times v will give us our v sub x. Cosine of 37 times 14.0 meters per second equals v sub x, which gives us a value for v sub x of 11.18089714 meters per second. We can only have 2 sig figs because of the angle, so our final answer is 11 meters per second equals v sub x. Problem number 3 is a slightly hairier non-perpendicular vector problem. You have two non-perpendicular vectors, and you need to resolve them into one resultant vector. Let's get started. Your dog has taken off on a toot and seems to be chasing some sort of small wild animal. In an attempt to follow and intercept the dog, you leave home and hike 1.45 kilometers, 20.0 west of north, Then turn and hike another 1.37 kilometers at 32.0 degrees south of west, where you find your ever-loving pooch, tired and ready to go home. The trick part of this is, what straight line displacement can you and the pup take to get home? We'll get to that. You still have to find the resultant. While we're not solving this one graphically, doing a drawing that's at least somewhat to scale helps you get a visual cue on what you should have. So we'll pick a starting point, and I'm going to draw myself a compass rose. And I know that this individual is starting off at 20 west of north. So I'm going to make my first vector about there. And I know that the length of that line is 1.45 kilometers. Okay, from my second point, and I'm going to draw myself another compass rose, we turn at 32 south of west. So I'm going to draw that as about like that. And note that that line is not as long as the first one because the distance of that vector is not as long. So I'm going to go ahead and label that. That one is 1.37 kilometers. And of course we have a 32 in there, and we have a 20 in there. Drawing this as our overall picture gives us a better idea of where to put our resultant. I'm going to put the resultant in red, despite the fact that I'm not going to do the calculations in red because I think it's too hard to read. Our resultant connects the head and tail of the first and last vector. Now, a couple things to note. In this problem, you're being asked about the displacement to get home. So we would expect that vector to run like this. But aside from that, whether you looked at it in the homeward travel direction or in your overall displacement to where you were, you still have to find the magnitude of that resultant. Now, the other issue that I've seen on these is people really want to make this a 90-degree triangle and not go through all the hassle. They want to say, well, that's 90. Whether it is or not, and it's not, doesn't matter. You have these are non-perpendicular vectors. It's not a 90. You can't force it to be a 90. So you still have to look for the two smaller triangles and then the larger overall. Let's do that. It's sometimes easier to find the overall first because you've got the hypotenuse of the overall triangle. That's what your resultant vector is always going to be. So I'll go ahead and draw these in with a dotted line. We know that we have an overall y there and an overall x there. That one's not quite done. There we go. So just aside from any concern about what direction those vectors should be in, if we're going home, of course they should be like this. Those are the overall x and y. So now let's look at our initial triangles to see if we can figure out where those are. So the y displacement for our first leg of our journey is there, and it's very clearly upward. And the x displacement is there, and it's very clearly westward. Now, for the second leg of the journey, our x displacement, having a hard time getting that one centered where I want it, is there, and our y displacement is there, very clearly downward. So in other words, our y displacements are in opposition to one another. Your final drawing should look something like this. Now let's lay out the math. I sometimes find it helpful as a reminder to myself to note right off the bat that my resultant is going to be equal to the square root of my resultant x and my resultant y, both squared. It's a helpful reminder to me that I have to find the resultant x and the resultant y. So let's set about doing that. I'll start with my first triangle, and I'll start with delta x1. Well, noticing that delta x1 is across from opposite that 20-degree angle, I know that delta x1 is going to be the sine of theta times 1.45 kilometers. In other words, delta x1 is 0.495929208 kilometers. And just to help myself out, I'm going to give myself a little arrow as a reminder that it's headed that direction. Delta y1, because it's adjacent to this angle, is going to be something that we find using the cosine of theta. So cosine of 20 degrees times 1.45 km, and delta y1 is equal to 1.3625543 km. And again, I'm going to help myself out by giving myself an arrow to remind me that this is displacement on the y-axis in the northward direction. Great! I'm ready to start with my second triangle. So when I look at my second triangle, I notice that now my delta x2 is adjacent to my angle. So delta x2 will be something that I find using cosine. So cosine of theta times 1.37 kilometers will give me my delta x2, and that gives me a value for delta x2 of 1.161825892 kilometers. Again, I give myself some help by putting in a little arrow as a reminder that it's headed west. Delta y2, because delta y is opposite my angle, is going to be found using sine of theta times 1.37 km. So that gives me a delta y2 value of 0.725989.392 kilometers. And so that I don't screw something up, I'm going to go ahead and give myself a little arrow there to note that that is in a southward direction. Okay, now we're ready to find delta x resultant and delta y resultant. So, delta x resultant is equal to delta x1 plus delta x2. That's easy. Delta x resultant equals 0.459, etc., plus 1.161, blah, blah, blah. The little arrows tell me that these are in the same direction, so I know that they're not in opposition to one another, and I'm going to go ahead and just add them. So my delta x resultant is equal to 1.65775, etc. That's kilometers, and this whole value is still westward. Okay, now I'm ready for my delta y resultant, which does have a few things that you need to be careful with. So just as in the case of delta y resultant, delta x resultant, delta y resultant is equal to the sum of delta y1 and delta y2. The trick, however, is that these are in opposition to one another. So delta y1 is north, while delta y2 is south. So we're going to have to make one a negative. It's easiest to make the smaller number a negative, so you get an absolute value. Okay, we have delta y resultant there, which is equal to, again, you can choose to subtract these, you can choose to make one a negative, Either way, you know that they're in opposition, so the value of y resultant is going to be less than the value of your largest one here. Okay, when you do this correctly, you get a y resultant value of 0.63656490 blah 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 kilometers, and of course this is northward. Now we're ready to look at getting our resultant. The other thing to note, I've noted these as northward and westward. They are, but remember, we're going to turn this around to get the route home, so don't panic too much about that yet. Remember this, that thing we started with? Time to use it. Let's go. The resultant here is equal to the square root of the x displacement squared plus the y displacement squared. R is equal to the square root of 1.65 etc. squared plus 0.6365 etc. squared, giving us a value for our resultant of, I feel like there should be a drum roll, 1.775772185 kilometers. Fantastic! Now we just have to get our heading. So, we're always looking for the angle between the resultant and the first vector. But since the problem, so normally we would say this angle, because that's what we're looking for in terms of our resultant, normally, this angle, because that gives us our resultant to get to where we are. It's our resultant displacement. But in this case, we're looking for the angle to go home. So we're thinking about this final vector with an arrow on it this way, which means we can do one of two angles. We can either do this shallow angle here or this deeper angle here. Now, I've chosen to do my vectors on the outside of this triangle. Remember that vectors can always be moved parallel to themselves, so we could just as easily take this, stick it here, and take this and stick it there. It's the same triangle, it's the same resultant. I did it on the outside because it's a little bit neater to do that way. Let's go ahead and keep it on the outside for the purposes of calculation. So for our purposes here, theta would be equal to the inverse tangent of its opposite over its adjacent, which would be tan minus 1 of delta xr, delta x resultant, divided by delta y resultant. That gives us an angle of 68.993603, etc. degrees. Now the big question is, what's our heading? Well, if we were taking this angle, that heading would be towards the east from the south. So that would be 69 degrees. I'm sorry, we do get 3 sig figs. 69.0 degrees east of south. You could, of course, also take 21.0 degrees south of east by taking this angle. Okay, we've only got one more to go. Hold on. Last problem. In the process of navigating the halls of BLHS, you head due west for 4.5 meters, then turn 35 degrees west of north and walk for 5 meters, before turning and heading due west again for 2.5 meters to exit the building. What's your overall displacement, magnitude, and heading? So though this problem has 3 legs, only one of those vectors has both an x and a y component. Your first travel is 4.5 meters due west. Then you need to draw yourself a compass rose, because the next leg of your journey is 5 meters at 35 to the west of north. So that's going to look something like that. Remember to put arrows on your vectors. The final leg of your journey is another one that's all on one axis, and that is traveling 2.5 meters due west. So where's your resultant vector here? Well, the resultant here sort of crisscrosses everything else. And the resultant for this will end up, whoops, looking like that. That means that your resultant triangle is going to look something like this, with this as your delta x resultant and this as your delta y resultant. As is always the case, your resultant is equal to the square root of delta x squared plus delta y squared. So we're going to note that and then set it aside while we find delta x resultant squared, while we find delta x resultant and delta y resultant. Let's start off with the basics. Delta x1, delta y1. Well, this is pretty easy because all of the first leg of travel is on the x-axis. So delta x1 is equal to 4.5 meters, and delta y1 is equal to 0. Fantastic. Now, the one that has both an x and a y component is the second leg of travel, where we have delta y2 and delta x2. Being as that this is our angle, and that this is a 35-degree angle, our x measurement is opposite that angle, so we're going to use sine to find our delta x2. So delta x2 is equal to the sine of theta times 5.0 meters, and that's of course the sine of 35. So delta x2 is equal to 2.867882182 meters, and I give myself the arrow as a reminder that this motion is still west. If we look back to our drawing, we'll notice that delta y2 is adjacent to the 35-degree angle. So delta y2 is equal to the sine of theta times, cosine of theta times 5.0 meters. Theta is, of course, 35, giving delta y2 a value of 4.00957602221 meters. And again, I give myself an arrow as a reminder that that motion is northward. With the third leg of our journey, we're back to the easy stuff, because of course all of that third leg is on the x-axis. So delta x3 equals 2.5 meters, and delta y3 equals 0 meters. And again, I'll give myself an arrow as a reminder that that motion is westward. So we have a delta x resultant of delta x1 plus delta x2 plus delta x3, and we can actually just borrow these. We get a value for delta xr of 9.8678821 meters to the west. So delta yr is really easy. Delta yr is equal to delta y1 plus delta y2 plus delta y3, and we know already that two of those have a value of 0. So delta yr is really, essentially, equal to delta y2. So delta yr equals 4.09876, etc., and that's in a northward direction. Now we have to go back to our big triangle. So r is equal to the square root of 3.8678821 meters squared plus 4.09876, etc. meters squared, giving r a value of 10.68411,674 meters. With sig figs, of course, of which we only have 2, r will become 11 meters. Now, let's figure out that heading. So, we notice that delta y resultant is opposite the angle, and delta x resultant is adjacent to the angle. So we're going to be using an inverse tangent function, and since tan is opposite over adjacent, we'll have delta yr over delta xr. Let's plug that in. So taking the angle this way, we get a theta value of 22.541368. Of course, that'll be a theta of 23 degrees. Now, what's our heading? Taken this way, that's a heading of north of west. We can always use the complement, and if you drew in your resultant triangle like that, you'd be taking this angle with your x as your opposite and your y as your adjacent. That would give you a heading of 67 degrees west of north. Either one is acceptable. Neither one is more correct than the other. Just make sure that you are sure which angle you're taking and what that heading should be like. So your final answer is 11 meters at 23 degrees north of west, or 67 degrees west of north. That's it. Keep working.